And there was A, B, C, D, and E. We're going to assume 15 points, probably looking at 3 points apart. There's probably some of them that are more and some that are less, but on average, when you're working this problem, if you can't do a part of this, it's probably a letter grade reduction for each part you can't do. So you figure if you can't do E and it was worth 3 points, the best you can get is a 12. You've now lost a 5 and you're down to a 4. If you can't do D, you lose another 3 points, you're down to a 9. You are at the threshold between a 3 and a 4. So as we start looking at the point totals here, one of the things I want you to do on the next mock exam is immediately when the mock exam gets posted, put this on the side of your paper, a scratch paper. This is for the mock exam. And as you go through the exam, when there are things that you feel like you can nail, put a check mark. And when you feel like there's things that you really don't know where to start, put an X. And don't sweat this. Don't try and make it more complicated. A check or an X. Do it just for the mock exam, because when you're done, what I'm hoping you will have are the specific things that you need to have starting points for your resource paper. So on the mock exam, whether we do it together or whether we do it at 11 o'clock today, do this. So we got 15 minutes until the 11 o'clock run. So let's get started with taking a look at this problem. We did this differently, so there are some things that we're going to have to talk about here that were different than the way we did the lab. We've got this clamp here. This mass is going to be dropped. If we assume that the pulley is relatively massless, I'm not sure we can make that assumption, but let's, for the time being, assume it is. Then the tension that's in the cable is, I should be drawing some of this. There, we have a mass like that. And this is going to our apparatus, which has, it's like just a T of PVC pipe. So if we assume that this is massless, and I'm not saying it is, if we just assume it is for this moment, the tension here and the tension here is going to be the same. So we have, in essence, a modified Atwood machine. That's what it really is. The only difference is instead of pulling a weight across the table, we're going to be spinning this PVC system. So it says briefly identify each quantity to be measured, the symbol used to represent that quantity, and the equipment that you would use to measure that quantity. You could have attacked this two different ways. You could have attacked it through conservation of energy or through force and torque. Based on the equipment I have in a classroom, I would probably measure the acceleration, because I can use a motion sensor down here at the ground, which I could then get a velocity versus t graph. And from here, I could plot that to get the acceleration. This seems like the way I would do it. So I'd probably get acceleration here and compare that with the angular acceleration I'd get here from timing it. Meaning I would time how many rotations it makes. Now, it says briefly identify each quantity to be measured, the symbol used to represent that quantity, and the equipment that would be used to measure that quantity. That's probably what I would get. Now, we could do it another way too. We have access probably to the mass of this weight. That's something else we could measure. And for those of you who would prefer even lower tech, we could measure this displacement and measure the time. Now, I'm not saying all of these are things that we would measure. I'm saying these are some of the things you could measure. So when I start listing out the things that could be measured from this, it's in an attempt not to be vague, because you guys said that the person that was there was vague. It's just demonstrating the things that we have measured in the past and the things we would use to measure it. We need to make sure that we are not complacent here. It says briefly identify each quantity to be measured. That's one thing, each quantity to be measured. The symbol used to represent that quantity, that's a second thing that each thing has to do, and the equipment that would be used for that quantity. So for each thing that I have listed here, I have to indicate what I'm measuring, what symbol I'm using, and how I'm measuring it, with what equipment. So if you didn't do that on yours, if you didn't hit all three of those things for each of the things you were going to measure, it's wrong. Doesn't answer the question. Hold on. Pull the chat window. In this case, is alpha and the linear acceleration directly related by r? No. And, well, let me say it different. It depends what you call r. There's the r associated with that little tiny blue diameter there. And then, of course, there's this r. Now, I'm thinking the only r that matters in this problem is the one down here. That's probably the only r that's going to matter in this. And you're exactly right, Wes, by saying if you want to do it that way, this alpha and this a are related by this r. They would count as one variable. So let's consider that's something we can measure. We can measure that directly by using a motion sensor. We're talking about measuring a or alpha, and we're talking about the acceleration, the system's acceleration. So that's the first thing we can measure. The other thing we can measure is the mass that's dropped. And for that, I would just use a scale, or it's probably stamped on it. You know, we don't have to do anything more than that. I mean, if you really want to drive it home, you'd say that you'd measure a scale. We are going to need to measure r. And this is the radius of the tube. And meter stick is the worst way to, but that's probably what you have. You know, you want to sound like you're really smart, say calipers. But as we demonstrated in class, most of us couldn't figure out the calipers. So, meter sticks work. If you wanted to measure it other ways, you could talk about measuring the height that the weight drops, or delta x. And this would be the height, and this is for you guys who did it using energy. You could also do some timing stuff here. You can measure, say, lowercase t, or time to drop, t, and you use stopwatch, or number of rotations. What would we call this? This would be oscillations or rotations. There's not a great symbol to use here, so you just make one up. I'm going to say number there, and this would just be counting. So not all of these are necessary for this problem. We're going to hone in on the ones that we want for our lab. So if you decide to do this in terms of energy, well, you probably were pretty focused then on trying to figure out that height. And you might have even added one more here, which would have been the velocity of the system at the end. That's harder to do, though. And I want to be careful there. If you measure the velocity, I'd be very interested to see what you did to try and indicate you were measuring velocity. Because if you said motion sensor, the problem with using a motion sensor to measure the velocity of this system is the simple fact that the velocity is always changing because it's under acceleration. So you might be able to get a v versus t graph and measure out the velocity right as the block hits the ground, but it's going to be tough. It's going to be tough. It's not going to be easy. And in your description, you're going to have to be very clear about how you came up with that velocity. So question A says, briefly identify each quantity to be measured, but please point out you do not have to list all the things here that we measured, because not all of these are necessary. If I'm looking to figure out the moment of inertia of the pipe, if that's my goal, then I'm using delta tau equals I alpha. That's where the moment of inertia of the pipe is. And that's what they're talking about. Students are using a forming experiment to figure out I. I'm getting the acceleration and the net torque by looking at other things. So the acceleration is coming from the A of the system, which is easy to measure, this. The torque's a little bit more challenging, because the torque I'm going to have to get through a combination of trying to figure out the tension. That doesn't mean I won't have that, because I know that net force on the mass is going to equal MA, and this is ideally going to be mg minus tension equals MA. So I have a method to get the tension, and therefore I have a method to get the torque. So there's a lot of things to put together here, but since I'm going to look at the problem from the standpoint of torque and acceleration, I would have to have this, and this as the things that I would be measured, and they would have to be in my part A. So to get full credit for A, all three of those variables would have to be there, and how you were going to measure them, with the equipment you're going to use and the symbol you're going to use. Now, I want to be careful. Your answer to A only gets full credit if, when your answer to B is complete, it explains how all three of these things are going to be used. If question B doesn't refer to all of the things that are here, or refers to things that aren't here and you didn't describe them, you're not going to get full credit for A. So question B and question A are definitely intimately linked, as is question C. So just so you guys know, you probably need to be thinking about question C, which says which quantities calculated from your measurements in part B could be graphed on a horizontal and vertical axis to produce a graph that would be used to determine a rotational inertia. That's probably the first question to actually answer, in your head at least. That's going to lead to which one of these sets you're going to want to actually talk about. So for our question C, yeah, I know I'm skipping around, but you don't have to do these in order. I want to point out that this might be better working a little backwards, even if it's just on your scratch paper for a minute. Because question C says which quantities calculated from your measurements could be graphed on the horizontal and vertical axes to produce a graph that would be used to determine the rotational inertia. And then it says explain how you'd use your measurements to calculate those quantities. Well, the only place I appears is, there. So if I want to figure out what to plot, I need this on the y-axis and this on the x-axis, and the slope is going to be the moment of inertia. So that's exactly what I want to say for question C. I would need to calculate the net torque acting on the PVC pipe and put that on the y-axis. And I want the angular acceleration of the PVC pipe. I'm going to put that on the x-axis. And then I would say the slope of this line is going to be the moment of inertia of my PVC system. It says explain how you would use your measurements to calculate the quantities you graphed. That's the part that we have to be careful about. That's where I explain from what I measured where I'm going to get these. So I would start with the net torque. I know the net torque, there's only one torque acting on the system. That's the tension times the radius. So do I have tension and radius? No, but I am able to measure this with my meter stick. So how am I going to get the tension? I'm going to get the tension from the net force acting on the mass that's falling. Don't think I did my algebra right. It's mg minus tension equals ma. Yeah, that's right. That's right. So there it is. So that's how I'm going to get my tension. Of course, to get that means I need to get the acceleration. Where am I getting my acceleration? I'm getting the acceleration directly off the graph of v versus t from my motion sensor. Because I chose to use a motion sensor. Now, you have to write this as a paragraph. You can't write this as a, like I'm drafting it down here. This is just my scratch paper. And I'm scratching out the notes real fast before I start typing it up, looking at what I'm going to have to say. So now I'm preparing my answer for question C in my head. I'm going to plot the net torque versus the angular acceleration. The slope of that line will be the moment of inertia if net torque is on the y-axis and acceleration is on the x-axis. Boom, I've said which quantities calculated from my measurements in part B could be graphed on a horizontal and vertical axis to produce a graph. Now I need to explain how I would use my measurements to calculate these quantities. So, starting with net torque. I would say the net torque is the product of the tension and the radius of the pipe. I'm measuring the radius of the pipe using the meter stick, but the tension I'm going to get by looking at the net force acting on the mass, because tension is one of the forces that acts on the mass. And I would then say the two forces acting on the mass are tension and weight, and they're going to equal the mass times the acceleration of the mass. I can write this, it's a simple equation, into my paragraph, starting with mg minus t equals ma, and then manipulating it to get t equals mg minus ma. And then my last piece here would be I'm going to use the acceleration that I am calculating from monitoring the fall of the mass using my motion sensor. Now, that gets me just the y-axis, which was kind of complicated. But the x-axis, less complicated, because all it is alpha. And I will say, since I already have the linear acceleration of the mass, it is related to the angular acceleration of the PVC. It's related through the radius. So if I divide the angular acceleration by the radius, I'll get the, if I divide the linear acceleration by the radius, I'll get the angular acceleration. I don't want to spend a lot of time on this because I'm actually out of time. But when you're describing a procedure for a graph, procedure for a lab, the two biggest things you have to be able to explain is how you're reducing error and how you're going to reduce human intervention in the experiment. Because error isn't just human intervention. So multiple time trials is always the best way to go for anything that humans have to measure, especially using a stopwatch. But ultimately, there's other things you want to talk about. Careful placement of the mass, making sure everything starts the same way each time and is released from rest. Those kinds of things are things that tend to be missed, but they're things we would talk about in the class. All right, it's 11 o'clock. We're going to stop right here.